Hello everyone, my name is Ferhat Karakoç. In this video, I will present our work titled Linear Complexity Private Set Intersection for Secure Two-Party Protocols. This is a joint work with Alptekin Küpçü. In this work, we introduce a new private set intersection protocol which allows construction of secure two-party protocols that takes the intersection as an input. I will first share our motivation and give some information about the building blocks we used in the construction of our protocol. Then, I will present our protocols for private set membership, batch oblivious programmable pseudorandom function, and private set intersection. A two-party private set intersection protocol is a protocol where there are two parties P1 and P2 having their own sets and they want to learn the intersection without leaking any information about their items that are not in the intersection. In the classical private set intersection functionality, the parties input their set to the functionality and one of the parties outputs the intersection. Sometimes, a function of the intersection is desired instead of the intersection itself. In this functionality, the parties input their sets and one of the parties outputs a function of the intersection. Private set intersection with oblivious data transfer functionality allows one of the parties to learn a function of the membership results between its items and the set of the other party. It is called oblivious since neither party learns the membership results, but they only learn function outputs. These functions can be, for example, encryption of the membership result. Actually, the membership result is just 1-bit information. These functions get the 1-bit information and, for example, outputs an encryption of it. The advantages of PSI with oblivious data transfer functionality is that it allows construction of secure two-party protocols that outputs a function of the intersection. It is not possible to do this with classical PSI protocols because they reveal the intersection to at least one of the parties. These functions can be one-time paid encryptions of the membership result, which allows the parties to learn the secret shares of the membership results. These functions can output corresponding wire labels for the membership results, which allow one of the parties to learn the wire values that will be inputs to a Garbot circuit-based two-party secure computation protocol. Also, these functions can be a public key encryption of the membership results under the sender party's public key, where the encryption scheme can be a homomorphic encryption scheme, which allows performing some computations on the encrypted membership results. Our motivation is to construct a private set intersection protocol that allows construction of larger secure two-party protocols that get the intersection as an input. In literature, there have been some solutions for this requirement such as the PSI protocols proposed by Ciampi and Orlandi and the circuit-based PSI protocol by Pincus et al. The Ciampi-Orlandi protocol is based on oblivious graph navigation and has O and log n over log n communication and computation complexities. The protocol of Pincus et al. Is based on oblivious polynomial evaluation and achieves linear complexity only for communication. Our aim is to introduce a PSI protocol with oblivious data transfer, with linear communication and computation complexities. Note that although there have been PSI protocols in literature with linear complexities, they don't achieve this functionality and simply reveal the intersection. To achieve the linear complexity aim, we utilize the usage of Garbot Boolean filters. Oblivious transfer is one of the widely used building blocks in secure multi-party protocols. It was first introduced in 1981. In this setting, the sender party P1 has a message pair and the receiving party has a choice bit B. After the execution of the protocol, the receiving party only learns the corresponding message based on its choice, and nothing about the other message. At the same time, the sender learns nothing about the choice bit of the receiver. In the construction of oblivious transfer, public key techniques are used, which makes the oblivious transfer protocol slow and costly. Fortunately, the oblivious transfer extension methods speed up the execution of many oblivious transfer executions by enabling realization of many OOTs using a custom number of oblivious transfers, called as base oblivious transfers. Private set membership functionality is similar to the private set intersection functionality, but here one of the parties inputs an item instead of a set. In the a function of PSM functionality, one of the parties learns a function of the membership result. In the secure equality testing, two parties input an item each to test the equality of the items, and one of the parties learns the equality result. In other words, one bit information about the equality. The output can be a function of the equality relation instead of the equality result itself. In our construction, we consider this functionality, that is, the output is a function of the equality result. In our private set intersection protocol, we utilize the private set membership protocol of Ciampi-Orlandi. Note that this PSM protocol becomes an equality testing protocol if the set of party P1 includes only one item. A Bloom filter, introduced in 1970, is a representation of a set of n items with an m-bit string. In the transformation, k independent hash functions are used. The filter is set to 0 at the beginning, then hash outputs for the item is computed to reach the indexes, and then the cells in the filter indexed by the hash outputs are set to 1. A Garbot Boolean filter is similar to the Boolean filter, but the cells indexed by the hash outputs are set the secret shares of the item. Using a Bloom filter, a PSI protocol can be constructed as follows. P1 constructs a Garbot Boolean filter for its set X. P1 constructs a Bloom filter for its set Y. Then they run OTs for each corresponding cells in the filters. In other words, for the ith oblivious transfer execution, P1 sets the message pair as the string in the cell and 0. And P2 sets the choice bit as the bit in the ith cell in the filter. After the OT execution, P2 learns the secret share if the cell is 1. After running m oblivious transfers, P2 XORs the corresponding received messages for its items and checks whether the results are equal to the items. An oblivious pseudorandom function is a two-party protocol where party P1 holds a secret key k, party 2 holds a string x, and at the end of the protocol, P1 learns nothing, while P2 learns f of x under the key k, where f is a pseudorandom function family that gets a key k and an input string x and outputs a random-looking result. An oblivious programmable pseudorandom function is similar to the OPRF, except that in OPPRF, the protocol outputs predefined values for some of the programmed inputs. An OPPRF can be constructed using private set intersection protocol based on Garbot Boolean filters, by putting the secret shares of the associated data of the programmed values in the Garbot Boolean filter, instead of the secret shares of the items. Cuckoo hashing is a primitive that allows to map items of a set to the bins in a table, where there is at most one item in each bin. This primitive employs a few hash functions that maps the items to the bins of the table. The number of bins, that is, the size of the cuckoo table, is ON. A PSM protocol can be efficiently converted to a PSI protocol using cuckoo hashing as follows. P2 constructs a cuckoo table, and P1 constructs a hash table for their items. For the construction of hash table, each hash function is applied to each items, and the items are put to the bins indexed by the corresponding hash outputs. Note that each bin in this hash table may contain more than one item. The maximum size of the bins in the hash table is O log n over log n. To prevent the information leakage, the bins are filled with random numbers to reach the maximum size. Then, for each bin, a PSM protocol is executed. Note that with this approach, using an ON complexity PSM protocol, a PSI protocol with O n log n over log n can be constructed. In this work, we provide a new private set intersection protocol that can be used in larger protocols that gets the intersection as an input. As side contributions, we introduce a new private set membership protocol and a new batch oblivious programmable pseudorandom function. As I said before, an OPPRF protocol can be constructed using PSI based on Garbled-Bloom filters. In the construction of Garbled-Bloom filter, the secret shares of the associated data of the programmed values are put to the corresponding cells in the Garbled-Bloom filter instead of the secret shares of the items. We construct our PSM protocol using this OPPRF protocol and applying a secure equality testing protocol to the output of the OPPRF. Note that here the set protocol outputs a function of the equality result. Thus, our PSM protocol outputs a function of the membership result. To achieve a linear complexity PSI protocol, we need to execute many OPPRF protocols in a batch manner. To reach to the goal, we use only one Boolean filter and one garbled Boolean filter. Here, for each set xi, different random numbers, that means different associated values, are chosen by P1. And P2 learns the associated value Ri if yi is in the set xi. Otherwise, P2 learns a different random number for its item yi. Using these primitives, we construct our PSI protocol as follows. First, P2 and P1 computes a KUKA table and a hash table respectively. Note that the number of bins are On, where n is the number of items in the sets of P1 and P2. Assume that for each bin, P2 computes a Boolean filter and P1 chooses an associated value R and computes a garbled Boolean filter. Note that the size of the filters for each bin will be O log n over log n, since the size of the bins in the hash table is O log n over log n. Then, for each bin, they execute oblivious transfers where P2 learns corresponding associated values or different random numbers depending on the membership. After that, the parties run ON set protocols in parallel. In this way, the complexity of our PSI protocol becomes O log n over log n, since the number of bins are On, and for each bin, O log n over log n OT executions are performed. To achieve the linear complexity, we utilize our batch OPPRF protocol. Here it seems that the sizes of the Boolean filters need to be O n log n over log n, because the total number of items in the hash table is On times O log n over log n. That is the size of the bins in the hash table. But note that many of the items in the hash table are garbage values, and the total number of actual items is n times number of hash functions used in the KUKA hashing. Thus, the total number of actual items in the hash table is On. This requires Boolean filters of sizes On instead of O n log n over log n. This observation is the main observation that enables us to achieve the linear complexity in our protocol construction. The set protocols are applied in a similar way to the output of the batch OPPRF. Through having Bloom filters with linear sizes and running set protocol O(n) times, we achieve the linear communication and computation complexity. As a conclusion, in this work we introduce a new linear complexity PSI protocol that can be used as a building block in larger two-party secure computation protocols. Note that there are PSI protocols in literature that achieve linear communication and computation complexities, but they cannot be used in larger protocols since they reveal the intersection. To the best of our knowledge, our PSI protocol is the first protocol that achieves the linear complexity both in communication and computation in the membership function setting that we consider. Our observations show that Garbled Bloom filters can be investigated more as future works. Questions are very welcome during the live session and by email. We thank you for listening and your interest in our work. Thank you.